So this presentation is about columns and how we want to analyze and examine columns for this class. Basically, columns are essentially vertical members. They support compressive loads that are coming down from above, and certainly they are a major structural building component. Failure, in the case of columns, usually means catastrophic disaster. So they need to be designed correctly. Some of the considerations with columns is, number one, what kind of material are you making it from? The column could be a material such as steel, or it could be concrete, or we might even have columns made of wood. Another consideration then would be the length of the column. How long is it? How tall is it? Is it a short, fairly stubby column, or is it a much longer column where we have other considerations? The size of the columns, or the size with even the geometry of the column comes into play. How wide is it? How narrow is it? And those sorts of things. And finally, we need to be aware of the end conditions. How is it fixed at the top and at the bottom? Is it fixed very stably, or can it rotate, and how might that affect our considerations? So basically we can break our discussions into two groups: short and stubby columns and long and slender columns. So with short and stubby columns, basically we're looking at a crushing load. So basically the column is not going to bend or deflect, it's going to crush in some particular shape, as a case like this. So here what we're interested in is what is the overall crushing strength of that particular material. It's quite different when we get to long and slender columns. Here our concern is about buckling. What might happen with buckling? So we have, with long and slender columns, we have a much greater length. The column is much taller. And potentially we have the distance, or the distance on the short axis, is much smaller. So what we have to be concerned about is this displacement that we describe as buckling and that kind of phenomenon. Now, in the case of short, stubby columns, here's an example: short, stubby wood columns. And we can look at them with this particular formula, with this description, where F sub A is equal to P, the actual load applied, divided by the area. And that has to be less than capital F sub A, or the allowable compressive stress. Well, P over A is our formula for stress, what we're familiar with, as in pounds per square inch or something of that sort. So if we know what our P is, we can size our A, or the area, so that we have sufficient bearing area on that column, on the short stubby column, so that the value of F sub A here is less than the allowable compressive load. So it's often a matter of determining the area required. How wide and how wide is it? How thick is it? So that P actual is over A, F sub A. All right. In the case of buckling, we have long and slender columns, and of course the buckling will occur along the axis of the shortest dimension. So if this were something like a 2x4 or a narrow steel column, it's going to buckle along that short axis. And buckling, as far as the definition goes, it would be defined as uncontrolled lateral displacement of the column, at which point no additional load can be supported. And we have to remember that even if we think everything is loaded symmetrically, loaded at the center, there are certainly going to be eccentricities in terms of how the load is really going to be placed, and also certain irregularities of the materials, which are going to cause the buckling. And much of this is related to the slenderness ratio. Slenderness ratio basically being the length divided by the narrowest dimension. So, in terms of the buckling load, again, this is going to be, of course, related to the deflected shape. Here we use Euler's formula, and Euler's formula comes down to two factors, E and I. E is, again, comes back to our modulus of elasticity, or what is the stiffness of the material. I would be, what is the I, the moment of inertia in the minimum direction. So if we have this column right here, we have two axes, the y-axis and the x-axis. So which one is going to be, in which case is it going to buckle? And it will be strongest along on the x-axis and weakest along the y-axis. So here is our formula for Euler's equation. P critical is equal to pi squared multiplied times E, the modulus of elasticity, times I, the minimum, and that's all divided by L, the length of the column, and L squared. So in terms of the buckling load, so we have here P critical, pi squared, EI minimum over L squared. So this shows some of the examples of how it would be. So here's our slenderness ratio. As we get more and more in this direction, we're into a case where we have to be concerned about buckling. On the other side here, we're really more concerned about crushing loads. Here, this formula would apply P over A, so that has to be less than F critical, or the allowable crushing load for the material. Alright, so some things related to the slenderness ratio. We have two sort of scenarios. One is for steel and one is for timber. One consideration are the end conditions. How is it fixed at the top and the bottom? And another condition is what is the effect? What effect does length have? The length of the, and also what about the size? The size. This would be the cross-sectional area, or the size, the geometry of the column. So we have L, case of the brace column length. We have K, which is the effective length factor. R is another point that comes into it, R being the radius of gyration with respect to the axis of buckling, and D is equal to the least lateral dimension. Okay, so here's an example of our column, a 4x4 column, and we have a load, say it's carrying this load. And now some of the considerations is how is it fixed at the bottom here, and also how is it fixed at the top. So in terms of the effective length factor, which relates to how the column is actually attached or fixed at the top and the bottom. If K is equal to 1, then we're assuming that it's pinned at the top and the bottom, and that the effective L is over the whole length or the height of the column. So basically it can rotate freely as soon as any load is applied. So that would be K equal to 1. This is another scenario here where it's fixed or at the bottom, so it can't rotate very easily at that point. Fixed can, but it can rotate as a pin connection at the top. So in this case, we have a shorter effective length. K is equal to 0.7 in this case, And then what about the case where it's fixed at the top and the bottom? And here we have k equal to 0.5 for that. All right, another factor that we use in terms of buckling is the radius of gyration. It's hard to provide a very good definition for the radius of gyration, but basically it's a measure of the inertia with respect to the area. And of course, this comes back to we're going to have two axes here. So here we have this I-beam. We know that it's going to buckle more along this axis, this way, as it's shown here, and not the other axis. So we have R sub x is equal to I sub x over A versus R sub y, which is, the square root of I sub x over A. And we have R sub y is the square root of I sub y over A. So the least radius of gyration represents the weakest response to buckling, or the place that buckling is most likely to occur. Now that we have some idea or concepts of how we look at buckling, what sorts of things can we do about it? Well, primarily what's being done, or what can be done, is lateral bracing, that basically limits the effective length. So you have lateral bracing along here. We know that this is liable to buckle out like so. So if we brace it here, what we've done is basically shorten the distance where buckling can occur. So now we have this distance, or we have this distance, but not the overall distance. So therefore we've shortened effectively we shortened the length of the column with respect to its buckling response. All right, we have two planes of buckling, and both should be checked. We have the strong axis buckling, and we have the weak axis. Shows here examples here with the I-beam, and again, it's more likely to buckle if we think of it sort of in this terms right here. So if we have, say, the strong axis, we could probably use this whole length. So we're not as likely to be worried about buckling along that axis. But here we have the weak axis, so therefore we have to support it along the weak axis in the center of the column length. All right, some other things related to steel columns. When the column gets short and stubby, the F sub y will limit the load. F sub y being the allowable stress in crushing. All right, so we have three situations. One where K times L divided by R is less than 40. Here we have sort of the crushing response. This would be in this particular zone right here. So the column here is behaving as a short, stubby column, and we're looking at crushing. Between 40 and 120, which really relates to this zone right here, we're something in between. We have both crushing and we have buckling. We have to be concerned in a sense on both of those. And between 120 and 200, we're in this range right here. In this case, we're really dealing with long columns and potential for buckling in those columns. For timber columns, we have a different sort of examination. Here's our slenderness ratio, L, the length of the column divided by D1, where D1 would be the narrower axis. So D1 being the smaller dimension. Now, if we have, say, the short stubby column, here we have something on the order of F sub C equal to P over A, and it has to be less than or equal to the F sub C, which is allowable compressive stress, parallel to grain. One of the things about wood is that it has a much higher crushing strength parallel to grain than perpendicular to grain. So here we have the factors that come into play in this, F sub C being the compressive stress parallel to grain, P being the axial force on the column with the load, A being the cross-sectional area, and F sub C prime, as it's shown in this formula, the allowable compressive stress, and that's a factor that can be looked up in the wood handbook or something of that sort. All right, so just some practical or some real, in a sense, more real-world examination of columns. Of course, we see them in lots of different applications. Columns that hold up decks, columns that hold up very tall decks, and those sorts of things. What I'm showing here in this slide is something fairly unusual. Here is a house that was built, in a sense, built with OSB panels. The panels and no studs were used. So in a sense, the panel thickness, which I think was about 1 1/8 inch thickness, really represented a tall, very thin column. So you have the loads coming down here from the top of the from the roof and from the snow load that's going to be supported by the column over this whole top length, this whole length. Well, if you think about a fairly narrow column over this whole length, that's going to be much more difficult, and it's going to be a much too long a buckling distance. So in building this, you actually use your second floor, or the I-beam to support the second floor, is a bracing system. So this I-beam, as I'm showing with the pointer, actually extends over, attaches to this wall, and keeps that wall from buckling out or buckling in. So so in a sense, this flooring system ends up serving two functions. In addition to supporting the load up above, it also is the buckling support for this, such so that the height of this column is actually much less. Now, one wonders, okay, so why did we build a house like this, or why was this house built? One of the reasons for that is looking at a different type of basically weather protection and insulation system. Here it uses, here on the outside of the OSB, a membrane a peel and stick membrane is attached. That's basically your water resistant barrier. And on the outside of that comes your insulation, and then siding goes on top of all of that. So it's a different sort of system, potentially performs much better in terms of water management. But of course the challenge you have is this is a new system. So if it's a new system, how does it do with respect to supporting the loads and so forth? So along those lines, we set up and tested a bunch of short columns or short panels and looked at how well these panels could do. So we ended up putting these in a test machine. We built this particular jig. The load is then applied to the jig, to the column, and then the column is designed so it will buckle, because basically we want to test this column in as long a length as possible, but our machine only allowed us, say, 45 inches. So we ended up building it so that it could basically rotate at top and bottom in this manner, and in that way we basically induced some type of buckling response. And this would be so here it is here are the failed columns. And by the way, these columns were able to support anywhere, say, between 17,000 pounds and above that. So they're fairly rigid and fairly strong columns. But here's showing the columns after buckling. Here's showing how the OSB basically failed in this case. And in order to use the pin connection at the top and bottom, here we have it pin. Here we have the plate that the column basically sat in. Here's the pin's connection so it could rotate. So in this case, here we are. This is the way we set it up ahead of time. And the load would be applied. It rotates to facilitate the buckling of the column. In that way, we were able to make that kind of determination for the columns. So this wraps up what we have on columns. Thank you.